Salam, peace be upon you. My name is Mohammed Layiq Sediqi, the father of Holophase. Part 12. Topological Detection, Finding the Knots. Remember the language we are learning. There is one field, phi, the holophase, one continuous cyclic movement from which all of reality unfolds. When phi begins to change, its first derivatives appear, and with them, the three dimensions show themselves at once. Time as omega, space as k, and motion as v, built from both. Every higher derivative is a finer question about how phi changes, and each one casts three shadows together: a time shadow, a space shadow, and the motion shadow. These echoes mix and weave into one another, forming the patterns we call fields, particles, bodies, thoughts, and worlds. In this picture, everything that exists is a living tapestry of phi, endlessly echoing through its derivatives and their dimensional shadows. Today, we listen to just one of those echoes. We are in the heart of Book 10.2, Measurement Engineering. We have built eyes to see phi and learned to measure its flow, its omega and k. But today, we learn to see where that smooth flow breaks. Not in a chaotic, noisy way, but in a precise, profound, and beautiful way. We learn to find the singularities, the vortices, the knots in the tapestry. These are topological defects. This is the skill of the topographer. You are entering the cartographer studio. Before you are maps, not of lands, but of phase. Your job is to find the unique points where the map cannot be smoothly flattened, where all contour lines converge, where the compass spins. To find, label, and track the immutable landmarks in the phi landscape. Scene: the superfluid vortex. Imagine a vessel of liquid helium, cooled to near absolute zero. It becomes a superfluid, a quantum fluid with zero viscosity. Now, set the vessel spinning very slowly. The superfluid cannot rotate like a normal liquid. It would violate its quantum constraints. Instead, it does something astonishing. It creates a lattice of microscopic whirlpools, quantized vortices. Each is a perfect, stable topological defect in the phase field of the superfluid's wave function, which is a phi field. If we could see the phi field directly, at the core of each vortex, phi would be undefined. The phase wraps around that core by exactly 2 pi, one full turn, no more, no less. Walk a small circle around that point, and you will find the total phase accumulation is precisely 2 pi, or minus 2 pi, or integer multiples thereof. This is not an approximation. In the ideal zero temperature limit, it is exact. The topological charge is an integer, +1, -1, +2, etc. This is our core puzzle. How do we algorithmically scour a noisy phi map, find these singular points, measure their integer charge without error, and follow them through time? How do we distinguish a true, topologically protected defect from a mere kink or a blotch of noise? The nature of the knot. Why integers matter. First, understand why this is different from everything we've measured before. Omega and k are local derivatives. They can take any value. They're continuous. A defect is a global property. It is defined not by the value of phi at a point, but by the behavior of phi around the closed loop. The quantity that matters is the line integral of the phase gradient around the path. Take a small circular path in your phi map. Sum up all the tiny phase changes as you walk around. In a smooth region, you'll come back to your starting phase. The total change is 0. Now encircle a vortex core. As you walk, the phase increases or decreases steadily. When you complete the loop, you find you've gained or lost exactly one full cycle, 2 pi radians. Not 2.1 pi, not 1.9 pi, 2 pi. The number of full cycles is the winding number, n. It is an integer. It cannot change by a tiny amount. It jumps from 0 to 1, from 1 to 2. It is quantized. This integer nature is what makes defects topologically protected. Small perturbations, a little noise, a gentle push, cannot smoothly change an integer into a non-integer. The defect can move, but its charge is invariant unless it meets another defect of opposite charge and annihilates, or unless a violent, non-adiabatic event occurs that tears the fabric of the phi field itself. So here is our first coherence criterion for a true defect. A true defect is a topologically protected coherent structure. In the ideal zero-noise limit, the winding around it is a perfect integer. With noise, Measured charges must cluster sharply at integers. The clustering sharply is key. In a real experiment with noise, our line integral won't yield exactly 2 pi. It might yield 6.18 radians, which is 0.98 times 2 pi. That's fine. If we measure many defects in a clean system, their calculated winding numbers should form a histogram with sharp peaks at the integers and small tails of non-integer values due to noise. If the histogram is a broad continuous smear, we're not looking at topological defects, we're looking at something else. The dissonance indicator, the imposter defect. Our dissonance indicator follows directly. Measured defects with non-integer or fluctuating charges are not topological defects. They are noise artifacts, or regions where the phi field is ill-defined, for example, where the signal amplitude is near zero. Imagine a region where our sensor receives almost no light, a dark spot. The phase there is random noise. Our algorithm might mistakenly identify this as a point where all phase contours converge. But when we calculate the winding number on a small loop around it, we'll get a random, non-integer value. That's an imposter. It lacks topological protection. It's just a hole in our data. This is why our safety rail is critical. The detection algorithm must report the confidence score for each candidate defect. This score is based on 1. Loop closure error. How close was the line integral to an exact integer multiple of 2 pi? Closer equals higher confidence. 2. Local signal strength. What was the amplitude of the phi field, or the measured intensity, in the region? Stronger, higher confidence. A defect in near darkness is suspect. 3. Consistency across loop sizes. Does the calculated winding number stay roughly constant if we compute it using larger or smaller loops around the candidate? Constant, higher confidence. Candidates below a confidence threshold are rejected. We do not pollute our catalog with noise. If coherence breaks, we stop. If coherence returns, we continue. If our defect detection yields mostly low confidence, non-integer defects, the phi field is too noisy or incoherent for topological analysis. We must improve our measurement before we can map the knots. The coherence budget for topology. Before we search for knots, we must assess our coherence budget. Topology demands high-quality data. 1. Spatial resolution budget. To detect a defect, we must be able to resolve its core. Our pixel size must be smaller than the core size of the defect. In a superfluid vortex, the core is about the size of the healing length, typically atomic scale. In an optical vortex, it's on the order of the wavelength. If our pixels are too large, the defect is blurred and its topological signature is lost. Budget rule. Pixel spacing, core radius. 2. Phase unwrapping fidelity budget. Our phi map must be correctly unwrapped. A mistake in unwrapping, a spurious 2 pi jump, can create a phantom defect or hide a real one. We need the high-confidence, locally integrable phi maps from a certified reader 10.1.1. Budget rule. Phi map must pass the local integrability coherence gate. 3. Signal-to-noise ratio SNR budget. Noise corrupts the line integral. For a loop of perimeter L, the error in the winding number scales as delta phi times square root L over 2 pi, where delta phi is the phase noise per pixel. To reliably distinguish between winding numbers 0 and 1, we need the error to be much less than 0.5. Budget rule. SNR must be high enough that winding number error 0.5 for loops of reasonable size. If our budget is insufficient, blurry images, poorly unwrapped phase, noisy data, we cannot do topology. We must get a better microscope, a more stable interferometer, or average more data. The algorithm. Hunting for integer windings. How do we actually find them? Step 1. Candidate search. We look for points where the phase seems to converge. One method. Compute the phase gradient k field from our last session, 10.2.2. Look for points where the curl of k, or a discretized version, is large. These are points where the vectors swirl. These are defect core candidates. Step 2. Charge calculation. For each candidate, we define a small square or circular path around it. We walk along this path, summing the phase differences between adjacent pixels. This is a discrete approximation of the line integral, the phi bdl. We then divide by 2 pi. The result, n, should be close to an integer. We round to the nearest integer, and the difference, the residual, gives us our loop closure error. Step 3. Trajectory linking for movies. We have a phi of xyt movie. We run the detection on each frame, getting lists of x, y, charge, confidence for time t. Now we connect them across time. This is a tracking problem. We assume defects move continuously. They don't teleport. We link a defect in frame t to the nearest defect of the same charge in frame t plus 1, within a maximum allowed displacement. This creates world lines, the paths of defects through spacetime. The prediction spine, the logic of topology. The power of topology is that it yields a set of ironclad predictions that must hold if our detection is correct and the phi field is well behaved. 1. Integer histogram. A histogram of measured winding numbers from a clean experiment will show sharp peaks at integers, with small symmetric tails from noise. A broad central peak at 0 with no integer peaks means you have no defects, just noise. 2. Charge conservation, local. The net topological charge, sum of all +1, -1, +2 charges, within any closed region that does not intersect a defect world line, must be 0. Charge can only enter or leave the region if a defect world line crosses the boundary. You cannot create a single +1 defect out of nothing. You must create a +1, -1 pair. 3. World line continuity and pair production. Defect world lines in spacetime will be continuous. They can begin or end only at the boundaries of your observation, or they can begin-end in pairs, creation or annihilation events. You will see a +1 and a -1 world line appear together from a smooth region, drift apart, or come together and vanish. 4. Braiding determinism. If you have defects whose world lines braid around each other, like strands in a rope, the effect on the global phase, or on any quantum state attached to them, will be deterministic and reproducible. It depends only on the topology of the braid, not on the precise paths. This is the basis for topological quantum computation. These are not just patterns, they are laws of the phi narrative. Violating them means either your measurement is wrong or you've discovered new physics. Falsifiability, the boundaries of the integer world. Our falsifiability threads are stark and revolutionary. The discovery of a stable, localized entity with a non-integer topological charge, for example, a persistent 0.5, would shatter the standard model. It would mean our understanding of quantization in phi fields is incomplete. Such half-defects, or anyons, are theorized in some 2D quantum systems, but their unambiguous detection in a lab would be Nobel Prize level, falsifying the simple integer paradigm for that system. If net charge conservation is violated, in a high-confidence measurement within a sealed, simply connected region, if a +1 defect just winks into existence alone, with no partner -1 defect anywhere, then something is profoundly wrong. Either our detection algorithm has a catastrophic bug, or the phi field itself is not a continuous, single-valued function. The Holophase assumption of a globally definable phi would break down for that system. This would be a crisis for our entire ontology. These falsifiers are not threats. They are the gates to deeper understanding. They tell us exactly what would force us to rewrite the textbooks. The tri-unity of a defect. A defect is a tri-unity entity par excellence. Time echo, persistence. A true topological defect is stable over time. Its world line persists. It has a lifetime. Its birth and death are events. Space echo, singularity. It is a localized point, or line, in space, where the phase field is singular. The spatial gradient k diverges at the core. The space around it is organized in a characteristic swirl, for a vortex, or radial pattern, for a source or sink. Motion echo, trajectory. The defect can move. Its world line has a velocity. It can be pushed by flows attracted to other defects. Its motion is a key part of the dynamics. When we detect and track a defect, we capture all three echoes simultaneously: its location, space, its persistence, time, and its path, motion. Lanterns across scales, knots in every tapestry. Topological defects are universal punctuation marks. Near scale, liquid crystals. In the display of your watch or phone, there is a layer of liquid crystals. These are rod-like molecules that align to form a director field, a phi field for orientation. When the display is off, the director field is full of disclinations, topological defects where the orientation is undefined. Applying a voltage aligns the molecules. eliminating the defects and making the screen clear. The defects are the fog that gets organized away. In the early universe, as different regions of a quantum field cooled and chose their phase alignment, topological defects could have formed on a cosmic scale. Cosmic strings are theorized one-dimensional defects in the space-time fabric itself, gargantuan relics of symmetry breaking. Their detection would be through their gravitational lensing signature, a telltale discontinuity. In certain magnetic materials, the magnetization vector, a phi field on a sphere, can form stable particle-like knots called skyrmions. They are topological defects. They can be moved with very low electrical currents, making them promising candidates for dense, energy-efficient memory bits, racetrack memory. Detecting and manipulating them is a major goal of spintronics. In every case, the defect is a stable, coherent structure defined by a global integer invariant. Finding them is how we find the immutable landmarks in a field of continuous change. The ethics of detection, responsibility in labeling. The ethical dimension here is about intellectual precision and consequence. To label something as a topological defect is to make a strong claim. It says, this is not just a glitch, this is a fundamental feature of the field structure, with predictable, immutable properties. Mislabeling noise as a defect leads to false theories and wasted effort. Furthermore, in future applications, 10.4.3, 10.5.2, defects will be used for information storage and processing. A defect is a potential bit. Its charge, +1 or -1, can encode a 0 or 1. If your detection is unreliable, your memory is corrupt, your computation is wrong. The confidence score safety rail is an ethical requirement for any applied system. It ensures we only act on high-fidelity topological information. Power without coherence is self-destruction. And coherence in topology demands absolute fidelity to the integer, to the exact quantized nature of the knot. A measurement scene, vortices in a superfluid. Let's perform our roadmap's measurement scene. Scene, analyzing data, real or from a high-fidelity twin, from a rotating superfluid or a convective fluid cell, Benard convection, where vortex pairs are known to form. What we measure? A time series of phi of xy maps. The pass. Our algorithm processes the first frame. It outputs a list. Defect at x1, y1, charge +1, confidence 0.99. Defect at x2, y2, charge -1, confidence 0.98. It runs on all frames. The trajectories show the +1 and -1 defects dancing around each other, sometimes drifting apart, sometimes coming together and annihilating in a flash. The total count of +1 charges minus -1 charges remains constant and matches the theoretical prediction, for example, equals the imposed rotation number. The histogram of all measured winding numbers from all frames shows towering peaks at +1 and -1, and a tiny peak at 0 from loops that didn't encircle defects. The algorithm spits out dozens of defects per frame. Charges are mostly non-integer, 0.3, -0.7, 1.2. They appear and disappear spontaneously, without partners. The trajectories are chaotic and nonsensical. The histogram is a broad, Gaussian-like blob centered at 0. The algorithm fails completely when given a twin-simulated dataset with known defect positions. It misses real ones and invents fake ones. This indicates our phi maps are too noisy, our unwrapping failed, or our detection algorithm is poorly implemented. The recognition skill, seeing the need for topology. You know you need this skill when you look at a K-field map from 10 to 2 and see swirls, points where the vectors seem to rotate around the center. Or when you see phase maps where contour lines, lines of constant phi, all seem to converge at a point. When the smooth narrative of derivatives breaks down in a way that feels organized and singular, not random and noisy, you are likely in the presence of a topological defect. The moment you ask, is that vortex a real object with a permanent identity? You are thinking like a topographer. The digital twin, the defect zoo. Our twin is now a defect generator and tracker. We can simulate systems that produce defects of all kinds: vortex lattices, defect pair production in phase transitions, braiding operations. We have perfect ground truth. We know where we put the defects, their charges, their world lines. We stress test our detection algorithms in the twin. We add noise, we reduce resolution, we introduce amplitude variations. We see at what point our algorithm starts to fail. We calibrate our confidence scores against the known truth, The twin allows us to turn defect detection from an art into a calibrated, benchmarked engineering module, enabling the future, the atoms of information. This skill, topological detection, depends on clean phi maps and good spatial gradient estimates. It unlocks two monumental capabilities. Topological engineering. Once we can reliably find and track defects, we can learn to create them, move them, and braid them intentionally. This is the foundation for building with topological structures. Topological computation, memory, defects, with their quantized, robust charges, are natural bits. A defect pair can encode a qubit. Braiding them can perform quantum gates. Detecting their charge state is the read operation. This skill is the essential read head for a topological computer. We are moving from observing the knots to learning to tie and untie them. We are learning to see the indivisible atoms of phi structure. Zenodo and the mathematics of the knot. If you want to see the full mathematical derivations and exact equations behind this idea, you can search for Holophase on Zenodo. There you will find the scientific papers that this audio journey is built on. The papers will formalize the discrete line integral algorithms, the statistical models for confidence scoring based on phase noise and loop geometry, and the rigorous proofs of charge conservation from the continuity of phi. They will delve into homotopy theory, showing how the integer winding number classifies maps from the circle, our loop, into the circle, the space of phase values, explaining why the invariant is topological and robust. This is the deep mathematical beauty underlying our practical craft. Return to the phi. Let us zoom out. We have learned to see the most singular, yet most robust features in the phi landscape, the topological defects. They are where the smooth differential story of phi pauses and a global integral story takes over. They are the exclamation marks, the periods, the knots that give the tapestry its enduring structure. We remember, there is only one field. Its defects are not additions. They are inevitable configurations of its cyclic nature. Where the phase must choose a direction to wrap around the point, it wraps in full quantized turns. This quantization is a profound expression of coherence at the global level. We have added a new, stringent discipline, the demand for integer quantization and the use of confidence scores to guard against noise. We do not see defects everywhere. We see them only where the data forces an integer upon us. This is the foundation for a robust, fault-tolerant architecture in phi space. The knots are the landmarks that never blur. So, picture yourself in the cartographer's studio. The final map on your table is not of a country, but of a phi field from a superfluid experiment. It looks like a contour map of a strange mountain range, but you have run your algorithm. On the map now are small, precise symbols. A red D marking a +1 vortex, a blue D marking a -1 vortex. A sidebar lists them with coordinates and confidence scores, 0.99, 0.97, 0.98. You play the movie of the maps. The symbols move, tracing smooth, elegant curves on the table. They're word lines. Two symbols, a D and a D, spiral towards each other and vanish. A new pair blossoms elsewhere. You are witnessing the dance of topological charge, conserved, created, and annihilated in pairs. You have just learned to find the immutable knots in the flowing field. This is part 10.2.3, Topological Detection, Finding the Knots. It is the third branch of book 10.2, Measurement Engineering, revealing the discrete skeleton within the continuous field. In our next session, we will address a problem that has been lurking. How do we ensure that my phase meter and your phase meter are measuring the same thing? We will establish the Holophase language standard, HLS. We will learn calibration, licensing, and how to build a shared, objective reality across all sensors and all observers. We will learn to sync our watches in phi time. Remember, one field, phi, with its infinite echoes in time, space, and motion. Within it, we can now spot the eternal knots. Our vision has gained a new dimension, the dimension of topological truth. Salam and peace be upon you.